Welcome to another tutorial, and today we will continue from where we stopped in the last class. In the last class, we actually stopped at forming matrices, representing system of linear equations in matrix form. And this was how we represented what we have here. What we have here, we represented it as this. So moving on from there now, let's now talk majorly on matrices. So matrices from here on now. So let's just have a subtopic. Let's just have it as matrices. So matrices plays a central role in linear algebra. They can be used to represent system of linear equations, but they also represent linear functions, that is linear mapping. We will later study this, probably today, in next class actually. Before we discuss some of these interesting topics, let's first define what a matrix is and what kind of operation we can do with matrices. So matrix basically, matrix is, let's say, m, n, element of real number, element of natural numbers. That's the count numbers that we have. Then we can say matrix A is an m.n tuple of elements where A, ij, where I equals 1, to m, and j equals I, to n. So we can say m is the number of rows while n is the number of columns. So basically our matrix is represented like this. A is equal to A11, A12, A1n, A21, A22, A2n. Then like that, we have AM1, AM2, AMN. Then we have . Let me make my lines bolder so we can see what I'm writing now. So we have our Aij, element of the real number line. Are you getting me now? So basically this is a representation of matrix. So let's have this to encompass the whole thing. So this is a representation of matrix. So we said with m, n element of natural number, a real value, that's a natural number is actually an element of real number line. So m, n matrix A is an m.n tuple of elements where Aij, where I is an Ai equals 1 to n, j equals 1 to m, which is ordered according to a rectangular scheme consisting of m rows and n columns. So basically in the conventional scheme of things, we call that's 1, n matrix are called rows and m, 1 matrix are called columns. That is, when you have this, we call this a column matrix, and when you have from here to here like this, we call it a row like that. So that's what we mean by m, n. So having our real number now, that's m, n. It's a real valued m, n matrix. That's m, n matrix. So that's about that. So moving on from there, let's just do some basic operations with matrices. So let's do matrix addition and multiplication. Remember when I was defining vector the other time, I said we can add two vectors together to form another vector, or we can multiply them by a scalar to form a vector of the same type. Then we call them what? A vector. So I'm using vector, I'm supposed to use objects. So when we can add two objects together to form a new object of the same type, or we can multiply the object by a scalar to form a new object of the same type, then we call it a matrix. So to add two matrices together now, that is, let's say we want to add A plus B. We want to add A plus B, we have, let's say our matrix A plus B is now 1, 1, plus B11 dot 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 A1n plus B1n, then dot dot dot, then we have AM1 plus BM1 dot 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 AMN plus BMN. So this addition of matrices now, we add them element wisely, that is element by element, we add them together like that. So that's how we add together two matrices. So that's basically like a element of the real number system of m by n, and our b element of the real number system of n by k. So element Cij is equal to, that's element Cij will be equal to element Aij plus element Bij. But now let's go to the product. That's multiplication of two matrices together. That is, let's say C, our C is now equal to A multiplied by B. Don't mistake this C with this C here. This C with this C. They are different ones. So let me just call this one the addition. Let me just use, let's say D here instead of the C, so that we won't confuse it with each other. So basically, our C. So our C will be, so Cij will be equal to summation L equals 1 to n of AIL BLJ. I know it's getting confusing right now, but follow me as I go on from here. So basically what we are saying is, let's say this is our A1 dot 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 AN dot 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 M1, yeah, dot 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 AMN. This A11. Let's have one here. So then we have B11 dot 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 BN1, right? B1N, sorry, it's supposed to be 1. Yeah, then we have AM1 to B, it's supposed to be B, that's BMN. So these are matrix now. So when we want to multiply two matrices together, we multiply them like this. We multiply this row by this column. So this times this, then this one times what the things that are here, then the last one times the last one. Then we now sum them together. That's what this equation is doing here. This equation that we have here, that's what it's doing. So we multiply this and this element wisely. That's this vector, this column, this row by this column. Then we now add each of the things we generate together. And that's how we generate new matrices. So Cij, we multiply elements of the ith row of A with the jth column of B, and then sum them up. That's basically what I just explained. And in the later section of our class slides, probably next week or the week after, you will understand that what we just did is what we call the dot product. That's when we say dot product, that's what we mean by A dot B. Don't mind the element-wise operation in in our computers, that we can multiply two rows, two columns together to form a new column. That's actually another thing entirely. We call that Hadamard product. Well, what I mean by Hadamard, this is Hadamard product. And what I mean by Hadamard product is when, let's say you have column A, column B, and you are now multiplying, let's call them X and X, Y. Then you are now multiplying, let's say X1, X2, X1, X2, X3, then Y1, Y2, Y3. Then you are now having Z1, Z2, Z3. where z equals x1 times x times y. So we are multiplying this by this to form this, this by this to form this, this by this to form this. This is different from dot product. This is what we call Adamad product. You will use it a lot when you are doing your data cleaning or when you are generating new columns in your machine learning algorithm. But that's not what we call dot product. Dot product is what I explained here, where you multiply the column by the row, and that's what we call the dot product, and that's how we multiply two matrices together. And you must have noticed something, that the two matrices must share in common to actually form and to be actually be multipliable. It means that the number of rows in the second matrix must be equal to the number of columns in the first matrix. What do I mean by this? See our A, see our B, which equals C. So n times K matrix, then we can have K times M matrix. Then it will now give us n times M matrix. What I'm saying is the number of columns here must be equal to the number of rows here. If they are not equal, then it will give us error while we are trying to multiply, because we have some remainders, and we can't have any remainder when we are multiplying two matrices together. So that's basically what I'm trying to explain. Here. So moving on from there, let me just give you an example of a matrix that we can multiply together to form another matrix. So let me open a new page. Let me get to the Adamad page and then open a new page now. So yes, let's say A is equal to 1, 2, 3, then 3, 2, 1. Then we have B is equal to 0, 2, 1 minus 1, then 0, 1. So it's easy for us to understand when we do an activity with it. So to form a new matrix now, to multiply A by B, to multiply A and B together, we would have, that's 1 times 0. So I need this screen to be bigger, but it can't be bigger than this. So let me just move to another screen entirely. So we say 1 times 0. So let me just draw that matrix in a small compartment here. 1, 2, 3. Then we have 3, 2, 1. This is our A and this is our B. That's 0, 2, 1 minus 1, 0, 1. So now, to form a new matrix now, this is how we do it. Follow me. So we have, for the first one, that's this particular point, we have 1 times 0, that's 1 times 0, which is 0, plus 2 times 1, that's 2 times 1, which is what? 2, plus 3 times 0, which is 0, this plus. Then the next one, that's coming here again now, we have this. You know that this place is 1, 1. That's why we have row 1 multiplying, that's row 1 multiplying colon 1. So to get this 1, so to get 2, that's 1, 2, we have row 1 multiplying colon 2, that's 1 times 2, that's 2. 2 times minus 1, that's minus 2. Then 3 times 1, that's 3, that's plus 3. So now to now get this point to that's 2, 1, then we now do colon 2 multiplied by, that's colon 2 multiplied by, yes, colon 2, row 2 multiplied by colon 1. That's 3 times 0, which is 0, plus 2 times 1, which is 2, then 1 times 0, which is 0. Then we have this multiplied by this to get this particular place now. So that's where we have 3 times 2, which is 6, minus 2 times minus 1, which is minus 2. Then 1 times 1, which is 1. So now this will now give us our newly generated matrix, which is 0 plus 2 plus 0, that's 2. Then 2 minus 2 plus 3, that's 3. Then 0 plus 2 plus 0, that's 2. Then 6 minus 2 plus 1, that's 5. So that's our multiplication of these two matrices. That's 2, 2, 3, 2, 5. And if you check back where we did here, if you check this place again, you will notice that I said n by k, k by m. That's our matrix here was 2 by 3 and 3 by 2. That's 3 by 2, which gives us 2 by 2. That's this by this. So that's basically what we just generated here. That's what we just generated here. Then we can multiply this by this again. We can multiply b by a. You know, this our, from here, this is our b, this is our a, this is our b. So we can multiply this the other way around. I'm just trying to prove to you that a multiplied by b is not equal to b multiplied by a. So now multiplying b by a, now we have, let me just write it, 0, 2, 1 minus 1, 0, 1. Then multiply by 1, 2, 3, 3, 2, 1. So to get our new matrix now, that will be this times this. That's 0 times 1, that's 0. 2 times 3 plus 6. Then the next one, that's 0, 0 times 2, that's 0. That's this place multiplied by this place now. That's 0 times 2, that's 0, plus 2 times 2, that's 4. Then the next one will be 0 times 3, that's 0. Then 2 times 1, that's 2. Then we have the next one, that's this place, multiplying this place now. So we have 1 times 1, that's 1, plus 1 times 3, that's 3. Then we have, no, sorry, that's minus 1 times 3, sorry. Let me use my eraser here. So that's minus actually. Then 1 times 2, that's 2. Minus 1 times 2, that's minus 2. Then we have the next one is 1 times 3, that's 3. Minus 1 times 1, that's minus 1. Then on to this line now. That's 0 times 1, that's 0. Then 1 times 3, that's plus 3. Then to the next one, that's 0 times 2, that's 0. 1 times 2, that's 2. Then 0 times 3, that's 0. 1 times 1, that's 1. Which is now equal to, yes, 6, 4, 2. Then minus 2, 0, 2. Then we have 3, 2, 1. You can see this here is not equal to what we have here. So that's a basic proof to you that that's a property of, there's a property of, what's it called now? A property of matrices telling you A multiplied by B. So let me just go to the next slide. Let me just go to the next page. A, B is not equal to B, A. It's not equal to B, A. That's basically what I just proved to you. This tutorial is already getting long, so I will stop here to come and explain the commutative. I mean, this one is what we call the commutative property. So our matrix is not commutative property. So see you in the next class, where I'll be explaining multiplication, identity matrices, and other types of other operations of matrices. We can have identity matrix, we can have inverse and transpose. So I'll be explaining that in the next class. See you in the next class. Thank you very much for joining today's class.